Hi, my name is Harvey Raja. I work as a part of the Coherence development team, and today I'm going to speak to you about a new feature we've added in Coherence 12c called Live Events. Coherence is a part of the Cloud Application Foundation group of products. It's a complete, open, integrated, and best-in-class set of products. These products can be hosted either in private clouds or in public clouds. Specifically, we're going to speak about live events in this talk. Let's take a look back at some of the eventing mechanisms that are available prior to Coherence 12c. So first of all, we have the map listener, and this is a client-side event. And just to explain the notion of client-side, generally in Coherence deployments we see that the architecture is a multi-tiered architecture. So one of those tiers generally is a storage-enabled tier, and that means all members a part of that tier will be responsible for owning data and managing partitions. There's also a storage disabled tier, i.e. a client tier, and the members a part of that tier will generally perform requests, things like storing data, put requests, or get requests, or queries, entry processors, aggregators. In addition, there may be clients as part of that tier that want to be reactive to changes that occur in the data grid. And so to provide that facility, we added an interface called a map listener, and that can be registered via the name cache API, via the method add map listener. And it can be a broad set of changes that want to be listened to, or a narrow set of changes. And whether it's broad or narrow is determined by a filter, or whether you specify to be very specific in terms of the keys that you are interested in. Are post events. The events are delivered asynchronously to the client nodes from the storage enabled node where the mutation is occurring. The mutation is committed on the storage node. This means that it's exposed, and any queries or entry processors or aggregators that are executed will see the new value. We also provide an existing event mechanism called a map trigger. A map trigger we call a pre-event. The reason we call it a pre-event is because it occurs prior to committing that mutation. Also, the map trigger is called synchronously. This means that the map trigger itself has an ability to mutate the value that's been sent to the map trigger. It also has the option to veto the underlying event. The veto is done by throwing some exception, which will then get propagated to the client. Backing map listeners are server-side events, and they are post events. They occur as we insert data into the backing map. And generally they should be short-lived, as they are synchronously called. And there are a number of other events that are worth noting here. So we have partition events, we have member events, and service events, each with their associated listeners. Partition events are raised when partitions are redistributed, specifically on members where the partition is departing from, and members that are new owners of this partition. Member events are raised when members join and leave the service, and service events are raised during the life cycle of the service. So let's look at some of the disadvantages of the previous eventing mechanisms. Now, first of all, there are distinct registration mechanisms per event type. So if you want to register a map listener, it's very different to if you want to register a backing map listener or a partition listener. The map listener is registered via the name cache API, as is the map trigger, but the backing map listener is registered via the Coherence cache configuration file. And as well as that, the partition listener, the service listener, and the member listener are all registered to either via the cache service or derivatives of the cache service. So there's no common means to register a listener regardless of the event type it's listening to. Okay, and as well as that, it kind of leads us on to the fact that each of the client interfaces, the callbacks, are all distinct as well and have no commonality between them, as well as the underlying events. And the semantics of the event are difficult to reason with. Are they synchronous? Are they dispatched synchronously or asynchronously? And do they occur prior to actually committing into the storage, i.e. the backing map, or after? And is it safe to do certain operations as a result? So we hope to alleviate some of those concerns with the new introduction of the live event model in Coherence 12c. And the reason we named it the live event model is because the events are delivered on the same node where the mutation occurred. So the event itself is the first interception point, and it's the first point in which the underlying mutation can be reacted to. We hope that this means that building event-driven architectures and event-driven applications is a little easier with coherence. So when we looked at the type of events that we wanted to deliver as the first release of this feature, the ones that we thought would be most capitalized on are things we could break into two buckets, the partition service level events and the partition cache level events. And each of those is each individual type of event. So if we look at the partition service, we have transfer events and transaction events. And the transfer event itself is all to do with partition redistribution. And we'll drill into each of these events in a bit more detail later on. The transaction events are actually cross-cache events. So when you have a partition local transaction and enlist many entries within that partition local transaction, you actually have a single event that's delivered now called a transaction event. And on the partition cache side, we have entry events which relate to puts or removes or updates. And an update is a put where a key is already present. And we also have the entry processor event, which enables the ability to react to an entry processor, i.e. a name cache invoke request, being invoked on a storage node. And like I said, we'll drill into each of these in a bit more detail. The other thing that the live event model has allowed us to do is homogenize our invocation, our registration, and our dispatching mechanisms. So future events can hook into the same framework very easily, and as well as that, the event interceptors, and from both a cache configuration or a client programmatic registration point of view, it's the same framework that's being registered to and the same APIs. So let's drill into a live event and specifically look at the data-related events. Here we can see that we have an entry event interface, and this is one of the data-related events delivered as a part of the live eventing model. The entry event itself extends another event interface, and that's a super interface across all live events delivered as a part of the live eventing model. The event itself takes in a generic, and that generic is an enum type. And we can see that enum type is defined further in the interface. This enum type defines all the various forms that the entry event may take. So the entry event may be delivered as an inserting, inserted, updating, updated, removing, or removed event. In addition, the entry event also receives a set of binary entries. Now, these are all the binary entries that were mutated as a part of the event and are delivered via the entry event. The entry event is actually delivered to an event interceptor. An event interceptor is analogous to a map listener. It's the implementation that will be registered with the live eventing model that can react to the underlying event. And we'll actually have a demonstration later on to look at this. Additionally, it's worth noting the difference between the pair of events under the entry event enum type. So here we have a pair which is inserting and inserted, and either one of the pair will either be a pre or a post event. And whether it's pre or post can be inferred by the suffix of the type. So here the inserting event is a pre-event and the inserted event is a post event. Whether it's pre or post means that there are certain things that can be assumed or not assumed. So with the pre-events, we deliver the event synchronously prior to committing the mutation that occurred that triggered this event. As for the post event, it's delivered asynchronously on a different thread to the one that's actually performed the mutation. And the mutation has already been committed. It also affects the binary entry that's returned. So within a post event, the binary entry that's provided as a part of the event is immutable, whereas for the pre-event, it can be modified. So similar to map triggers, pre-events can can veto the underlying mutation. So within an inserting, the event interceptor could throw an exception, and that exception would be propagated back to the client, and the mutation would not be committed to the underlying store and ultimately the backing map. So let's have a look at how this would actually work from end to end. So here we have a client that's executing a name cache put. So they execute the put, the request gets sent to the storage node, and we execute the inserting UEM entry event, and that gets sent to the event interceptor. When the event interceptor returns, we then insert the binary into the backing map. And we then dispatch the post event, asynchronously dispatch the inserted. We also asynchronously dispatch the backup as well. Now we still hold on to the client thread, so we don't return to the client until the backup completes. And once it does complete, we then inform the client, who then returns from the name cache put call. And let's have a look at the entry processor event. So very similar to the entry event in regards to the actual interface definition. We have a type which has the executing executed, and you can see that we also have the entry set and it's binary entry based. But in addition, we also have get processor. So we actually get the entry processor provided to the event. Okay, and this is the same entry processor that we're about to call process all on. So let's take a look to see what this looks like end to end. So here we have the client, and this time we're issuing the name cache invoke. That gets sent to the storage node that owns the key that this entry processor is being executed against, and it then issues the executing to the event interceptor. The event interceptor receives the entry processor event of type executing, and it then responds. And once it's responded, we then invoke the entry processor, invoking process all with the same entry set that we delivered to the event interceptor. If the entry processor modified the binary value, then we insert the binary value into the backing map, and we dispatch the executed event and the backup, which eventually comes back to the client. And let's have a look at transfer related events. Again, the binary entry base. So here we can see the get entries method has a map of keyed by cache name to a set of binary entries. The reason for the map this time rather than the set that we had previously is that a partition may have multiple caches. Hence why they're keyed by cache name. The other thing worth noting here is that the binary entries themselves are immutable, and something that we didn't mention previously was that when it comes to the pre-events and the post-events, the pre-events receive mutable binary entries because they're invoked synchronously, whereas the post-events receive immutable binary entries because they are invoked asynchronously. And we can see here that the transfer event also exposes the partition ID in question and the local and remote member. The transfer event itself can also be of varying types. It can be a departing event or an arrived event. So when it comes to the departing event, the local member currently owns this partition, but the remote member will be the new owner of this partition, and the arrived event is when the local member is the new owner of the partition and the remote member used to own this partition, is also the source of the transfer. So let's take a look at an end-to-end example. So here we have two members of a partition service. They both have an event interceptor attached, and we have 64 partitions here. And that's 32 partitions each. And so a new member joins the service, a storage-enabled member. And the partition service coordinator decides that we should redistribute partitions so that they are distributed fairly. And so 11 partitions from each member are going to be redistributed to the new member. And so we dispatch UEM transfer events of type departing to the event interceptor. And when that event interceptor returns, we then transfer the partition. And they are now owned by the new member. But prior to committing that ownership, we dispatch the transfer event of arrived. And once the interceptor returns, we then commit the new ownership. And now let's take a look at transaction-related events. A transaction in these terms is a partition local transaction. And an event, the transaction event, is delivered for all entries enlisted within a partition local transaction. A partition local transaction is a feature that was added in Coherence 3.7.1, and it allows for entry processors or map triggers to enlist new entries into the local transaction. So the transaction event itself is binary entry based, and therefore the getEntrySet returns a set of binary entries. And the various types of the transaction event can be committing or committed. Again, these are pre and post respectively. The pre-event receives mutable binary entries, whereas the post-event receives immutable binary entries. It's also worth noting that the transaction event, it is capable to enlist new entries within this partition local transaction. However, the transaction event committing is a one-shot deal for this request. We will execute it once, and if a new enlistment occurs, we won't re-execute the committing transaction event. So let's take a look at how this would look end to end. So here we have a client, and the client does a name cache invoke call with the keys of A and B. And we assume that A and B have some affinity, so they land on the same partition. And the green member here is the owner of that partition. So the request gets sent with the entry processor to this member. And so we execute the entry processor with the original keys that were requested, A and B, and we call process all. The entry processor itself enlists C, which is also assigned to the same partition, and it would then return to the storage node. We then send the transaction event committing for all three, for A, B, and C, to the event interceptor. The event interceptor then returns. We then perform the committed and the backup as well, and return from the backup and then return to the client. So the rest of the flow is very similar to the entry event. And let's now take a look at registration and how one would register an event interceptor with the Interceptor Registry such that the event interceptor received events. So there are two mechanisms, either declarative or programmatic. The declarative mechanism uses the coherence cache configuration file, and there are two sections that accommodate interceptors, either the distributed scheme or the cache scheme mapping. The distributed scheme should really contain interceptors that pertain to partition service events, i.e. transfer event and transaction event. It can contain partition cache level events such as entry events and entry processor events, but they're not bound to specific caches, and any cache filtering that could be done in the cache configuration cannot be performed. In addition, interceptors can be defined in the cache scheme mapping section. The cache scheme mapping allows for the cache name filtering to be performed for the interceptor, and we'll take a look at an example of that shortly. In addition, we also use annotations and generics to filter the events of interest. So let's have a look at an example of both the annotations and the configuration. So here we can see that we have a cache name defined of vetoed events, and that maps to a scheme called the examples partition POF scheme. And here we can see that we have a cantankerous interceptor that's defined under this cache name. So the cantankerous interceptor won't be invoked for any other caches that are hosted by the examples partition POF scheme except for the vetoed events cache. Also, if we look a little further down, we can see that we have an interceptor defined under the distributed scheme, and that is the redistribution interceptor. Now that's a transfer event interceptor, therefore as it's only interested in the transfer event, it's correctly defined under the distributed scheme. If I take a look at the cantankerous interceptor, we can see that it's annotated now, and the annotation defines that it has an identifier of cantankerous, and this means that if I get a handle to the interceptor registry at some point in the future, I can have the particular instance returned to me via this identifier. We can also see that the cantankerous interceptor is not concerned with removed or removing events, and therefore it defines all the other events it's interested in. Let's have a look at the programmatic mechanism. So we have a new interface defined as part of Coherence 12c, and that is the Interceptor Registry. it's actually associated to a configurable cache factory. So every configurable cache factory will have its own Interceptor Registry. And the Interceptor Registry allows for clients to register event interceptors. Any annotations or generics on the interceptor are honored during the registration mechanism. And in addition, the interceptor itself can decide which services and caches it wants to restrict itself to, or either narrow or broaden itself to, via implementing the Event Dispatcher Aware interface. Okay, I think it's about time we have a demonstration showing you some of the features of live events and how easy it is to receive a live event and react to it. So here I've got my IDE and I've got a simple Maven project which is called Live Events Demo, and it has a couple of dependencies on JUnit and Coherence, 12.1.2. Also, the only other artifact I really have here is a Coherence cache config XML file, and we can see that it's named Coherence cache config XML file consciously, so that because I know source main resources will be ahead of Coherence jar in the class path, and I won't have to specify the Tanksol Coherence cache config JVM argument for every process that I start up. So here I have a very simple cache configuration file with unbounded scheme mapping, such that every cache will be hosted by the live events distributed service, with no other real configuration except to auto start it. So let's create an event interceptor. So we'll do a new Java class and we'll call it live events live event interceptor. Okay, and that's just a normal class, and so let's make sure we implement the correct interface, and that's the live event interceptor. Now there's a generic argument that's accepted by the event interceptor which narrows the type of events that the live interceptor will receive, as mentioned in the slides. And so let's restrict this to say that we are only interested in entry events. And let's implement the appropriate method. Now the actual implementation we're going to make pretty trivial. We'll output the actual event so that we can see where it gets output. Also, we'll actually, if we just go back here, I will also throw the thread name in as well, just so that we can see when we receive the pre and post events, we can see the difference. Okay, and the other thing that I think we should do is we should mutate the event. So if you recall, it's only the pre-events that you can actually mutate the binary entry. And so we need to be conditional on the pre-event, and for simplicity I think we'll just use the inserting event, and if we are in an inserting event then we should mutate it just to make sure that that functionality works as expected. So we'll get the type of the event and we'll see if it's a type of inserting, and if it is, well then first of all we'll assume that we only have a single binary entry by getting it from the entry set and simply getting the first entry, and the next thing we will do is set the value, and we'll set it to the previous value, the value that was requested. However, we will append our own string. Okay, so we have a live interceptor, we'll see all events, and for inserting events we're actually going to mutate the entry. So the next thing we need to do is register it within our cache configuration, and we're actually going to put this in our cache scheme mapping section. Okay, so here we can see that we have interceptors and we have the correct interceptor defined. The other thing that's worth noting is that I have a run configuration here. The run configuration is to launch a console, and the console is launched via cache factory. The only other thing I specify here is some VM args. Okay, so let's run this console. So this is going to start a single member, and it will start with the console. Now the thing that's worth noting about the console is it doesn't auto start services. Okay, so we can see that I joined the cluster, but none of the services have started, and they only start when you either call start server or you call ensure cache. And as I want to interact with the cache, I'm going to ensure the cache. So let's go into this test. Okay, and we can see that it's empty. And let's put an entry in here. Hi. Okay, so we can see that we output the event, so we can see we have the inserting event, which is actually delivered by this thread. And also we have the inserted event, which is actually delivered by this thread. Sorry, it's not very clear to see here actually, but it's this thread here. So that's the first thread, and this is the second thread. So we can see there's different threads delivering the events, the inserting and the inserted. The other thing we should see is if I list the contents of the cache, that the value was appropriately mutated. So here we can see that intercepted was appended onto high, which is great. So the other thing that's worth illustrating is if I start up a new console. Now we can see that there are two members of the cluster now, and like I mentioned, it's not going to start any of the services until prompted. So let's get it to join our dist test. So it joins the service. We can see that we don't really see any other log messages except that we join the service and we ask for a number of partitions and the configuration that was realized, but we don't see anything else. Now let's go back to my previous console and let's put another value in. And let's put 3 with the value of buy. Now we can see that we don't receive any of the system outs that the event interceptor should have. Now I've got two members of this service that are both storage enabled. Now the member we just started owns partitions of 0 to 127, and this member owns 128 to 257 because 257 is the default partition count. If I do a list, I can see that 1 and 3 are present and they have appropriately been intercepted. If I have a look at the other console, I can see that we have our inserting and inserted events that were intercepted on the node that owns the partition. Okay, and as you can see that the only events that we received were entry events. We didn't receive any of the other live events that we've mentioned previously. Okay, so let's stop this and kill these consoles. Okay, so the next thing I wanted to illustrate was, well, what happens if I don't want an entry event? I actually want a transfer event now. Okay, so let's change this to a transfer event. And accordingly, let's change the method signature. And we can remove this mutation code now. So I still have my live event interceptor, which implements event interceptor, but now it's only interested in transfer events. I have a cache configuration file, which has my live event interceptor. So nothing needs to change there. Now let's kick up a console. And as soon as it does, we will ensure the cache. Okay. So let's call it dist test again. We can see that we don't receive any events and therefore no output. And let's start up another console. So we start up another console. We don't receive any output on either console again. As soon as we join the service, we should see a certain output. Now, if we go back to the previous console, what we'll see is that there are a number of departing events that have been delivered for each partition. And if we go back to the new member, we can see that there are a number of arrived events that have been delivered for each partition. So what this illustrates is simply by changing the generic type, the generic argument to change the type from an entry event to a transfer event, the correct type of event is delivered. And we don't need to change any cache configuration at all. And equally, if I retire this member from the service, we see that this member delivers a number of departing events for each partition, and on the other member we receive a number of arrived events for each partition. Well, I hope that demonstration was beneficial. Please feel free to join us on the Coherence community. We have a Twitter account, a Facebook account. We have an RSS feed from the blog, which is often updated with interesting posts on issues that we see or hot topics. We also have a LinkedIn Coherence user group, and we have the YouTube channel, which hopefully you found because hopefully you're watching this video on it. Also, we have a global Coherence special interest group where like-minded individuals and coherence enthusiasts get together to discuss hot topics, new features, and from a development perspective, we get feedback from you guys, and hopefully you guys get to see what we're working on or learn how other organizations are using coherence as well. I've been Harvey Raja, talking about Coherence live events, a new feature in Coherence 12c. Thank you for listening.